Fiber-optic communication is a method of transmitting information from one place to another by sending pulses of light through an optical fiber. The light forms an electromagnetic carrier wave that is modulated to carry information. First developed in the 1970s, fiber-optic communication systems have revolutionized the telecommunications industry and have played a major role in the advent of the information age. Because of its advantages over electrical transmission, optical fibers have largely replaced copper wire communications in core networks in the developed world. Optical fiber is used by many telecommunications companies to transmit telephone signals, internet communication, and cable television signals. Researchers at Bell Labs have reached internet speeds of over 100 petabits per second using fiber-optic communication. The process of communicating using fiber optics involves the following basic steps: creating the optical signal involving the use of a transmitter, relaying the signal along the fiber, ensuring that the signal does not become too distorted or weak, receiving the optical signal, and converting it into an electrical signal. Applications: optical fiber is used by many telecommunications companies to transmit telephone signals, internet communication, and cable television signals. Due to much lower attenuation and interference, optical fiber has large advantages over existing copper wire in long-distance and high-demand applications. However, infrastructure development within cities was relatively difficult and time-consuming, and fiber-optic systems were complex and expensive to install and operate. Due to these difficulties, fiber-optic communication systems have primarily been installed in long-distance applications, where they can be used to their full transmission capacity, offsetting the increased cost. Since 2000, the prices for fiber-optic communications have dropped considerably. The price for rolling out fiber to the home has currently become more cost-effective than that of rolling out a copper-based network. Prices have dropped to $850 per subscriber in the US and lower in countries like the Netherlands, where digging costs are low and housing density is high. Since 1990, when optical amplification systems became commercially available, the telecommunications industry has laid a vast network of intercity and transoceanic fiber communication lines. By 2002, an intercontinental network of 250,000 km of submarine communications cable with a capacity of 2.56 terabytes per second was completed, and although specific network capacities are privileged information, telecommunications investment reports indicate that network capacity has increased dramatically since 2004. History: in 1880 Alexander Graham Bell and his assistant Charles Sumner Tainter created a very early precursor to fiber-optic communications, the photophone, at Bell's newly established Volta Laboratory in Washington, D.C. Bell considered it his most important invention. The device allowed for the transmission of sound on a beam of light. On June 3, 1880, Bell conducted the world's first wireless telephone transmission between two buildings, some 213 meters apart. Due to its use of an atmospheric transmission medium, the photophone would not prove practical until advances in laser and optical fiber technologies permitted the secure transport of light. The photophone's first practical use came in military communication systems many decades later. In 1966 Charles K. Cow and George Hockham proposed optical fibers at STC laboratories at Harlow, England, when they showed that the losses of 1,000 decibels per kilometer in existing glass was due to contaminants, which could potentially be removed. Optical fiber was successfully developed in 1970 by Corning Glass Works, with attenuation low enough for communication purposes, and at the same time GaAs semiconductor lasers were developed that were compact and therefore suitable for transmitting light through fiber-optic cables for long distances. After a period of research starting from 1975, the first commercial fiber-optic communication system was developed, which operated at a wavelength around 0.8 AA micrometer and used GaAs semiconductor lasers. This first-generation system operated at a bit rate of 45 Mbps with repeater spacing of up to 10 km. Soon on April 22, 1977, General Telephone and Electronics sent the first live telephone traffic through fiber optics at a 6 Mbps throughput in Long Beach, California. The first wide-area network fiber-optic cable system in the world seems to have been installed by Rediffusion in Hastings, East Sussex, UK in 1978. The cables were placed in ducting throughout the town, and had over 1,000 subscribers. They were used at that time for the transmission of television channels, not available because of local reception problems. The system is still in place, but disused. The second generation of fiber-optic communication was developed for commercial use in the early 1980s, operated at 1.3 AA micrometer, and used in GaAs-P semiconductor lasers. These early systems were initially limited by multimode fiber dispersion, and in 1981 the single-mode fiber was revealed to greatly improve system performance. However, practical connectors capable of working with single-mode fiber proved difficult to develop. By 1987, these systems were operating at bit rates of up to 1.7 GB per second with repeater spacing up to 50 km. The first transatlantic telephone cable to use optical fiber was TAT-8, based on de-Server-optimized laser amplification technology. It went into operation in 1988. Third-generation fiber-optic systems operated at 1.55 AA micrometer and had losses of about 0.2 dB per kilometer. This development was spurred by the discovery of indium gallium arsenide and the development of the indium gallium arsenide photodiode by Pearsall. Engineers overcame earlier difficulties with pulse spreading at that wavelength using conventional GaAs-P semiconductor lasers. Scientists overcame this difficulty by using dispersion-shifted fibers designed to have minimal dispersion at 1.55 AA micrometer or by limiting the laser spectrum to a single longitudinal mode. These developments eventually allowed third-generation systems to operate commercially at 2.5 bits with repeater spacing in excess of 100 km. The fourth generation of fiber-optic communication systems used optical amplification to reduce the need for repeaters and wavelength division multiplexing to increase data capacity. These two improvements caused a revolution that resulted in the doubling of system capacity every 6 months starting in 1992 until a bit rate of 10 terabytes per second was reached by 2001. In 2006 a bit rate of 14 bits was reached over a single 160 km line using optical amplifiers. The focus of development for the fifth generation of fiber-optic communications is on extending the wavelength range over which a WDM system can operate. The conventional wavelength window, known as the C-band, covers the wavelength range 1.53-1.57 AA micrometer, and dry fiber has a low-loss window promising an extension of that range to 1.30-1.65 AA micrometer. Other developments include the concept of optical solitons, pulses that preserve their shape by counteracting the effects of dispersion with the nonlinear effects of the fiber by using pulses of a specific shape. In the late 1990s through 2000, industry promoters, and research companies such as KMI and RHK predicted massive increases in demand for communications bandwidth due to increased use of the Internet, and commercialization of various bandwidth-intensive consumer services, such as video on demand. Internet protocol data traffic was increasing exponentially, at a faster rate than integrated circuit complexity had increased under Moore's law. From the bust of the dot-com bubble through 2006, however, the main trend in the industry has been consolidation of firms and offshoring of manufacturing to reduce costs. Companies such as Verizon and AT&T have taken advantage of fiber-optic communications to deliver a variety of high-throughput data and broadband services to consumers' homes. Technology. Modern fiber-optic communication systems generally include an optical transmitter to convert an electrical signal into an optical signal to send into the optical fiber, a cable containing bundles of multiple optical fibers that is routed through underground conduits and buildings, multiple kinds of amplifiers, and an optical receiver to recover the signal as an electrical signal. The information transmitted is typically digital information generated by computers, telephone systems, and cable television companies. Transmitters. The most commonly used optical transmitters are semiconductor devices such as light-emitting diodes and laser diodes. The difference between LEDs and laser diodes is that LEDs produce incoherent light, while laser diodes produce coherent light. For use in optical communications, semiconductor optical transmitters must be designed to be compact, efficient, and reliable, while operating in an optimal wavelength range, and directly modulated at high frequencies. In its simplest form, a LED is a forward-biased p-n junction, emitting light through spontaneous emission, a phenomenon referred to as electroluminescence. The emitted light is incoherent with a relatively wide spectral width of 30–60 nm. LED light transmission is also inefficient, with only about 1% of input power, or about 100 microwatts, eventually converted into launched power which has been coupled into the optical fiber. However, due to their relatively simple design, LEDs are very useful for low-cost applications. Communications LEDs are most commonly made from indium gallium arsenide phosphide or gallium arsenide. Because in GaAs-P LEDs operate at a longer wavelength than GaAs LEDs, their output spectrum, while equivalent in energy, is wider in wavelength terms by a factor of about 1.7. The large spectrum width of LEDs is subject to higher fiber dispersion, considerably limiting their bit rate distance product. LEDs are suitable primarily for local area network applications with bit rates of 10 to 100 Mbps and transmission distances of a few kilometers. LEDs have also been developed that use several quantum wells to emit light at different wavelengths over a broad spectrum, and are currently in use for local area WDM networks. Today, LEDs have been largely superseded by VCSEL devices, which offer improved speed, power and spectral properties, at a similar cost. Common VCSEL devices couple well to multimode fiber. A semiconductor laser emits light through stimulated emission rather than spontaneous emission, which results in high output power as well as other benefits related to the nature of coherent light. The output of a laser is relatively directional, allowing high coupling efficiency into single-mode fiber. The narrow spectral width also allows for high bit rates since it reduces the effect of chromatic dispersion. Furthermore, semiconductor lasers can be modulated directly at high frequencies because of short recombination time. Commonly used classes of semiconductor laser transmitters used in fiber optics include VCSEL, Fibre power copyright ROT and DFB. Laser diodes are often directly modulated, that is, the light outputs is controlled by a current applied directly to the device. For very high data rates or very long distance links, a laser source may be operated continuous wave, and the light modulated by an external device such as an electro-absorption modulator or Mach-Xener interferometer. External modulation increases the achievable link distance by eliminating laser chirp, which broadens the line width of directly modulated lasers, increasing the chromatic dispersion in the fiber. A transceiver is a device combining a transmitter and a receiver in a single housing. Receivers. The main component of an optical receiver is a photodetector, which converts light into electricity using the photoelectric effect. The primary photodetectors for telecommunications are made from indium gallium arsenide. The photodetector is typically a semiconductor-based photodiode. Several types of photodiodes include PN photodiodes, PIN photodiodes, and avalanche photodiodes. Metal photodetectors are also used due to their suitability for circuit integration in regenerators and wavelength division multiplexers. Optical electrical converters are typically coupled with a transimpedance amplifier and a limiting amplifier to produce a digital signal in the electrical domain from the incoming optical signal, which may be attenuated and distorted while passing through the channel. Further signal processing such as clock recovery from data performed by a phase-locked loop may also be applied before the data is passed on. Fiber cable types. An optical fiber cable consists of a core, cladding, and a buffer, in which the cladding guides the light along the core by using the method of total internal reflection. The core and the cladding are usually made of high-quality silica glass, although they can both be made of plastic as well. Connecting two optical fibers is done by fusion splicing or mechanical splicing and requires special skills and interconnection technology due to the microscopic precision required to align the fiber cores. Two main types of optical fiber used in optic communications include multimode optical fibers and single-mode optical fibers. A multimode optical fiber has a larger core, allowing less precise, cheaper transmitters and receivers to connect to it as well as cheaper connectors. However, a multimode fiber introduces multimode distortion, which often limits the bandwidth and length of the link. Furthermore, because of its higher dopant content, multimode fibers are usually expensive and exhibit higher attenuation. The core of a single-mode fiber is smaller and requires more expensive components and interconnection methods, but allows much longer, higher performance links. In order to package fiber into a commercially viable product, it typically is protectively coated by using ultraviolet, light-cured acrylate polymers, then terminated with optical fiber connectors, and finally assembled into a cable. After that, it can be laid in the ground and then run through the walls of a building and deployed aerially in a manner similar to copper cables. These fibers require less maintenance than common twisted pair wires, once they are deployed. Specialized cables are used for long-distance subsea data transmission, for example transatlantic communications cable. New cables operated by commercial enterprises typically have 4 strands of fiber and cross the Atlantic in 60 to 70 ms. Cost of each such cable was about $300 million in 2011. Source: The Chronicle Herald. Another common practice is to bundle many fiber-optic strands within long-distance power transmission cable. This exploits power transmission rights-of-way effectively, ensures a power company can own and control the fiber required to monitor its own devices and lines, is effectively immune to tampering, and simplifies the deployment of smart grid technology. Amplifier. The transmission distance of a fiber-optic communication system has traditionally been limited by fiber attenuation and by fiber distortion. By using optoelectronic repeaters, these problems have been eliminated. These repeaters convert the signal into an electrical signal, and then use a transmitter to send the signal again at a higher intensity than was received, thus counteracting the loss incurred in the previous segment. Because of the high complexity with modern wavelength division multiplex signals, the cost of these repeaters is very high. An alternative approach is to use an optical amplifier, which amplifies the optical signal directly without having to convert the signal into the electrical domain. It is made by doping a length of fiber with a rare earth mineral erbium, and pumping it with light from a laser with a shorter wavelength than the communications signal. Amplifiers have largely replaced repeaters in new installations. Wavelength division multiplexing. Wavelength division multiplexing is the practice of multiplying the available capacity of optical fibers through use of parallel channels, each channel on a dedicated wavelength of light. This requires a wavelength division multiplexer in the transmitting equipment and a demultiplexer in the receiving equipment. Arrayed waveguide gratings are commonly used for multiplexing and demultiplexing in WDM. Using WDM technology now commercially available, the bandwidth of a fiber can be divided into as many as 160 channels to support a combined bit rate in the range of 1.6 bits. Parameters, bandwidth or Euro distance product. Because the effect of dispersion increases with the length of the fiber, a fiber transmission system is often characterized by its bandwidth or Euro distance product, usually expressed in units of MHz/km. This value is a product of bandwidth and distance because there is a trade-off between the bandwidth of the signal and the distance it can be carried. For example, a common multimode fiber with bandwidth or Euro distance product of 500 MHz/km could carry a 500 MHz signal for 1 km or a 1000 MHz signal for 0.5 km. Engineers are always looking at current limitations in order to improve fiber optic communication, and several of these restrictions are currently being researched. Record speeds. Each fiber can carry many independent channels, each using a different wavelength of light. The net data rate per fiber is the per-channel data rate reduced by the FEC overhead, multiplied by the number of channels. While the physical limitations of electrical cable prevent speeds in excess of 10 gigabits per second, the physical limitations of fiber optics have not yet been reached. In 2013, New Scientist reported that a team at the University of Southampton had achieved a throughput of 73.7 bit per second, with the signal traveling at 99.7% the speed of light through a hollow-core photonic crystal fiber. Dispersion. For modern glass optical fiber, the maximum transmission distance is limited not by direct material absorption but by several types of dispersion, or spreading of optical pulses as they travel along the fiber. Dispersion in optical fibers is caused by a variety of factors. Intermodal dispersion, caused by the different axial speeds of different transverse modes, limits the performance of multimode fiber. Because single-mode fiber supports only one transverse mode, intermodal dispersion is eliminated. In single-mode fiber, performance is primarily limited by chromatic dispersion, which occurs because the index of the glass varies slightly depending on the wavelength of the light, and light from real optical transmitters necessarily has non-zero spectral width. Polarization mode dispersion, another source of limitation, occurs because although the single-mode fiber can sustain only one transverse mode, it can carry this mode with two different polarizations, and slight imperfections or distortions in a fiber can alter the propagation velocities for the two polarizations. This phenomenon is called fiber birefringence and can be counteracted by polarization maintaining optical fiber. Dispersion limits the bandwidth of the fiber because the spreading optical pulse limits the rate the pulses can follow one another on the fiber and still be distinguishable at the receiver. Some dispersion, notably chromatic dispersion, can be removed by a dispersion compensator. This works by using a specially prepared length of fiber that has the opposite dispersion to that induced by the transmission fiber, and this sharpens the pulse so that it can be correctly decoded by the electronics. Attenuation, fiber attenuation, which necessitates the use of amplification systems, is caused by a combination of material absorption, Rayleigh scattering, miscattering, and connection losses. Although material absorption for pure silica is only around 0.03 decibels per kilometer, impurities in the original optical fibers caused attenuation of about 1000 decibels per kilometer. Other forms of attenuation are caused by physical stresses to the fiber, microscopic fluctuations in density, and imperfect splicing techniques. Transmission windows. Each effect that contributes to attenuation and dispersion depends on the optical wavelength. The wavelength bands that exist where these effects are weakest are the most favorable for transmission. These windows have been standardized, and the currently defined bands are the following. Note that this table shows that current technology has managed to bridge the second and third windows that were originally disjoint. Historically, there was a window used below the O band, called the first window, at 800-900 nm. However, losses are high in this region, so this window is used primarily for short-distance communications. The current lower windows around 1300 nm have much lower losses. This region has zero dispersion. The middle windows around 1500 nm are the most widely used. This region has the lowest attenuation losses and achieves the longest range. It does have some dispersion, so dispersion compensator devices are used to remove this. Regeneration, when a communications link must span a larger distance than existing fiber optic technology is capable of, the signal must be regenerated at intermediate points in the link by optical communications repeaters. Repeaters add substantial cost to a communication system, and so system designers attempt to minimize their use. Recent advances in fiber and optical communications technology have reduced signal degradation so far that regeneration of the optical signal is only needed over distances of hundreds of kilometers. This has greatly reduced the cost of optical networking, particularly over undersea spans where the cost and reliability of repeaters is one of the key factors determining the performance of the whole cable system. The main advances contributing to these performance improvements are dispersion management, which seeks to balance the effects of dispersion against nonlinearity, and solitons, which use nonlinear effects in the fiber to enable dispersion-free propagation over long distances. Last mile. Although fiber optic systems excel in high bandwidth applications, optical fiber has been slow to achieve its goal of fiber to the premises or to solve the last mile problem. However, as bandwidth demand increases, more and more progress towards this goal can be observed. In Japan, for instance, EPON has largely replaced DSL as a broadband internet source. South Korea unregistered trademark SKT also provides a service called FTTH, which provides fiber optic connections to the subscriber unregistered trademark S-Home. The largest FTTH deployments are in Japan, South Korea, and China. Singapore started implementation of their all-fiber next-generation nationwide broadband network, which is slated for completion in 2012 and is being installed by OpenNet. Since they began rolling out services in September 2010, network coverage in Singapore has reached 85% nationwide. In the U.S., Verizon Communications provides an FTTH service called FiOS to select high ARPU markets within its existing territory. The other major surviving ILEC, AT&T, uses an FTTN service called UVerse with twisted pair to the home. Their MSO competitors employ FTTN with coax using HFC. All of the major access networks use fiber for the bulk of the distance from the service provider's network to the customer. Also in the U.S., Wilson Utilities located in Wilson, North Carolina, have implemented FTTH and have successfully achieved 1 gigabit fiber to the home. This was implemented in late 2013. Wilson Utilities first rolled out their FTTN in 2012 with speeds offerings of 2060/100 megabits per second. Their service is referred to as Green Light. The globally dominant access network technology is EPON. In Europe, and among telcos in the United States, BPON and GPON had roots in the FSAN and ITU-T standards organizations under their control. Comparison with electrical transmission. The choice between optical fiber and electrical transmission for a particular system is made based on a number of trade-offs. Optical fiber is generally chosen for systems requiring higher bandwidth or spanning longer distances than electrical cabling can accommodate. The main benefits of fiber are its exceptionally low loss, its absence of ground currents and other parasite signal and power issues common to long parallel electric conductor runs, and its inherently high data carrying capacity. Thousands of electrical links would be required to replace a single high-bandwidth fiber cable. Another benefit of fibers is that even when run alongside each other for long distances, fiber cables experience effectively no crosstalk, in contrast to some types of electrical transmission lines. Fiber can be installed in areas with high electromagnetic interference, such as alongside utility lines, power lines, and railroad tracks. Non-metallic or dielectric cables are also ideal for areas of high lightning strike incidence. For comparison, while single-line, voice-grade copper systems longer than a couple of kilometers require in-line signal repeaters for satisfactory performance. It is not unusual for optical systems to go over 100 kilometers, with no active or passive processing. Single-mode fiber cables are commonly available in 12 km lengths, minimizing the number of splashes required over a long cable run. Multimode fiber is available in lengths up to 4 km, although industrial standards only mandate 2 km and broken runs. In short distance and relatively low bandwidth applications, electrical transmission is often preferred because of its lower material cost, where large quantities are not required, lower cost of transmitters and receivers, capability to carry electrical power as well as signals, ease of operating transducers in linear mode. Crosstalk from nearby cables and other parasitical unwanted signals increase profits from replacement and mitigation devices. Optical fibers are more difficult and expensive to splice than electrical conductors. And at higher powers, optical fibers are susceptible to fiber fuse, resulting in catastrophic destruction of the fiber core and damage to transmission components. Because of these benefits of electrical transmission, optical communication is not common in short box-to-box, backplane, or chip-to-chip applications. However, optical systems on those scales have been demonstrated in the laboratory. In certain situations fiber may be used even for short-distance or low-bandwidth applications, due to other important features: immunity to electromagnetic interference, including nuclear electromagnetic pulses. High electrical resistance, making it safe to use near high-voltage equipment or between areas with different earth potentials. Lighter weight are important, for example, in aircraft. No sparks are important in flammable or explosive gas environments. Not electromagnetically radiating, and difficult to tap without disrupting the signal are important in high-security environments. Much smaller cable size are important where pathway is limited, such as networking an existing building, where smaller channels can be drilled and space can be saved in existing cable ducts and trays. Resistance to corrosion due to non-metallic transmission medium, optical fiber cables can be installed in buildings with the same equipment that is used to install copper and coaxial cables, with some modifications due to the small size and limited pull tension and bend radius of optical cables. Optical cables can typically be installed in duct systems in spans of 6,000 meters or more depending on the duct's condition, layout of the duct system, and installation technique. Longer cables can be coiled at an intermediate point and pulled farther into the duct system as necessary. Governing standards: in order for various manufacturers to be able to develop components that function compatibly in fiber optic communication systems, a number of standards have been developed. The International Telecommunications Union publishes several standards related to the characteristics and performance of fibers themselves, including ITU-TG 651, characteristics of a 51/125 micrometer multimode graded index optical fiber cable, ITU-TG 652, characteristics of a single-mode optical fiber cable. Other standards specify performance criteria for fiber, transmitters, and receivers to be used together in conforming systems. Some of these standards are 100 gigabit Ethernet, 10 gigabit Ethernet, Fiber Channel, Gigabit Ethernet, HIPPI, Synchronous Digital Hierarchy, Synchronous Optical Networking, Optical Transport Network. Tosalink is the most common format for digital audio cable using plastic optical fiber to connect digital sources to digital receivers. See also, Dark Fiber, Google Fiber, Fiber to the X, Free Space Optical Communication, Information Theory, Passive Optical Network. References: Encyclopedia of Laser Physics and Technology, Fiber-optic Technologies by Vivek Allen, Agrawal, Govind P. Fiber-optic Communication Systems. New York, John Wiley & Sons. ISBN A0-471-21571-6. Further reading, Keyser, Gerd Optical Fiber Communications, 4th ed. New York, McGraw-Hill, ISBN 9780703380711, Senior, John. Optical Fiber Communications, Principles and Practice, 3rd ed. Prentice Hall. ISBN 978-0130326812, External links, How Fiber Optics Work, The Laser and Fiber Optic Revolution, Fiber Optics, From Hyperphysics at Georgia State University, Understanding Optical Communications, and IBM Redbook, FTTX Primer, July 2008, Fiber Optic Transmission in Security and Surveillance Solutions, Fiber Optics, Internet, Cable and Telephone Communication.